The next set of systems we're going to look at on the aircraft have to deal with fire and overheat protection. This also is smoke, fire, smoke, and overheat detection and protection. And these are all covered in ATA Chapter 26. No matter if you're doing fire, smoke, overheat, it's all kind of in one, all covered in this one area. So the goal of fire and overheat protection is we have to detect it, and then we have to remove the threat, extinguish it. And that can be a couple things. We can directly extinguish the flame, the fire, by displacing oxygen. Remember the triangle of flame? You need fuel, you need oxygen, and you need a heat source, an ignition source. If we remove any one of those, we can get rid of a fire. So detection, then we're going to extinguish, is displacing the oxygen. Then shutting off removes the fuel source. It could also be removing the ignition source. Although typically the fire itself is its own ignition source once it gets going, right? It's rare that once it's initially ignited, after that it's going to be continuous, just like a jet engine. Once it's ignited, you don't have to run the igniters anymore. The flame in the combustion chamber continues to do it. Same thing with fire. So in the FARs, in the regulations, there are 6 key design requirements. If you go and look and read through, because I know you all love reading regulations, the portions of Part 25 that deal with transport aircraft design and construction, there are 6 design requirements. So the first is we don't want false warnings. They put that number 1. Okay? False warnings cause a lot of bad things to happen. Okay, people panic, plane has to get to the ground quickly, they mobilize fire trucks, things get delayed. So because we have to these are taken so seriously, false warnings can cause a lot of problems. It's kind of like the boy who cried wolf, right? That's the other part of it. If you have too many false warnings, people start to get complacent and they ignore the warnings that you're getting. The second is when we do have something, we want to be able to rapidly indicate that to the crew and tell them where it is. Right? You don't just want something that says fire and it doesn't tell you if it's an engine fire, if it's the left engine, or if it's the right engine, or if it's a cargo fire, right? Or landing gear fire. You got to know where it's actually happening in order to deal with it. The third is that as long as the fire or smoke or whatever signs of or overheat is present, that indication is going to continue, because we have to indicate once it's been taken care of, once it's been extinguished, or once it's been cleared. Okay, so that's our indication when the fire is out. It's going to stay on continuously until the point where it's been extinguished, and then our indication is going to go away. Okay? It has to have the ability to be tested with it built in, have a built-in test element to it, built-in test equipment. And it must be damage resistant and tolerant. One, you don't want it damaged by the fire itself, right? If it stops indicating because the indicator got damaged, that's probably not a good scenario. But other things are in normal use. It also needs to be durable and robust enough that it's not going to be easily damaged by normal operations. Okay? When we did the lab looking at the smoke detectors in the cargo bay, remember every one of them had a cage over the front of it. Those have to be there. That's not just, oh, we want to make it, less damage to our smoke detectors. It is, the FAA says you've got to protect them with a cage like that. So if you throw a bag or a box into it, it's less likely to damage the smoke detector. Okay. So these systems are going to look for fire, overheat in multiple different ways. So overheat detection, things are getting too hot. Rate of rise is they're changing too quickly, because a rate of rise, if something's heating up faster than it should, it means it's probably going to exceed a maximum value. We have things like flame and infrared detectors. Those aren't as common, but they're becoming more common. Okay, those are a newer technology. Smoke and optical detection, right? Smoke's a sign of fire. It's not the fire itself, whereas flame infrared is actually detecting the fire itself. Carbon monoxide falls under this. We don't have a lot of carbon monoxide issues on big aircraft. Most don't even have carbon monoxide detectors because there is no combustion source going into the aircraft. Remember, we're pulling bleed air off the compressor of the engine before fuel and ignition are introduced. So it's not like a combustion heater like you have in a small aircraft where you're burning fuel inside of a heat exchanger to try to warm up the air that's going to go into the cockpit. And then finally, combustible mixture detection, another one that's fairly new. But these are used in a lot in cargo aircraft that are carrying hazardous materials in particular, is it monitors, we can monitor the atmosphere in the cargo compartment to make sure, say you're shipping something that can give off a potentially explosive gas, you can make sure it's not leaking and mixing with air. The other area you'll see these in some cases inside fuel tanks to make sure fuel vapor isn't creating an explosive mixture. So different areas for fire, we look at our engines, cargo holds, and lavatory. For smoke, cargo holds, lavatory, and cabin. Most cabins don't have a fire or a smoke detector. Most cabins, it's on the crew. You have a cabin crew that sees somebody, smells smoke or something like that. Overheat along ducting, leading edges of wings. We want them to get hot, but not too hot. The cargo holds and then the landing gear. And then combustible mixture, I've got cargo holds, although I've heard recently there's some talk about combustible mixture detection in the fuel tanks now too, in addition to gas inerting systems. So fuel tank inerting systems that prevent it from becoming a combustible mixture. The detectors that do this, the different components, is we have to have some kind of a sensing element, loop, spot, optical, infrared, etc. We've tested all these on our board. Those will tie into a control unit or a computer that controls and monitors what's going on. And then that's going to put out a signal to the crew if there's something amiss. So things like indicator lights, bells, horns, messages, other oral warning, that. And then finally, remember, there's that requirement for built-in test equipment, so the test circuitry itself. So this is a very simple version where we have a loop with our monitoring circuit. And normally, it's looking at a couple things. So the first is this monitoring circuit, it's going to make sure that it can send a signal all the way around. And that's going to tell it, that's going to allow it to determine whether that loop is in good shape or not. If this loop, remember these loops have the center core, they're going to ground out. If this gets a break in it, it will still work, right? If it gets a break in it, you'll still be able to pick up a ground on this end. You'll say it got broken here, or on this end. But if it gets two breaks in it, you'll have a dead spot in the loop. If it gets a break in it over here and a break in it over here, and then you get a hot spot here, you'll never know it. So it's constantly monitoring, do I have continuity from one end of the loop to the other? And that tells it that it can sense the entire length of the loop. Okay. The other thing it has is this test circuit. If you move the switch, for instance, in this case, that breaks the loop. So it says, okay, I can detect if there's a break in the loop, which is a caution type situation. And then the other thing the test circuit often will do is put a ground on there, which simulates that, like eutectic salt melting and causing a ground. So then it can detect the actual warning function of the loops. Okay. Remember, there's two primary types of loops they have to be damage and break tolerant, but they are still fragile in some respects. If you crush one of these loops, it's done. Or if you bend it too tight, they have minimum bend radiuses. If you bend it too tight and it kinks the outer shell, your loop is going to be shorted out. So you have your what's known as a Fenwal style, a single wire in the middle, eutectic salt, and a grounded in-canal tube around the outside. Okay. Or the double kitty style, which has thermistor, which is another type of compound, your wires, and then you get continuity between the wires if it warms up, if it gets too hot. Okay. Everyone knows how do you remember kitty versus Fenwal? What's that? Kitty's got two D's, the two circles for kitty, right? But just know that Fenwal makes kitty style loops and kitty makes Fenwal style loops now. The patents on these things have long ago gotten so they all do everything now. But that's just who developed each one originally. It doesn't mean they're the only ones making them today. And there's other companies too. Liebherr makes loops and systems. I think, I can't remember if Honeywell does. I don't know for sure, but Now these loops, for redundancy's sake, often run, you'll have multiple loops running in parallel. So you can see two along here. This is called a support tube. It's just a metal tube that's got brackets mounted to it. Where this is held, you can see these are little rubber grommets that go inside of the clips. That is so that the loops don't chafe on the mounts. It also does another element to make sure you don't get a hot spot where that little bracket is. These brackets are made of metal, and this might be running, say, around an engine. The engine itself is going to get hot, right? And the analogy I use is an oven. Hopefully some of you have cooked something in an oven at some point. If you have an oven and it's heated up to 450 degrees, if you open that oven, you stick your hand in just right in the middle of it, do you get burned right away? You can stand there and hold your hand in there for a period of time. It's not going to hurt you, right? What if you touch the rack in there? You're going to almost instantly get burned by it. That is, so heat or metal parts in a warm area concentrate heat and transfer heat directly into whatever touches them. So if this tube and these brackets are warm, and these loops are made to sense heat in the air, if you don't have those rubber grommets there, you're going to get hot spots everywhere one of those little metal things are. So that's a common failure point, is you'll be getting indications and you'll realize that one of those grommets fell out, or the grommet wore out and fell apart. Okay. The other one is these will be around the engine. When you close the cowl, you won't realize that it's touching the metal on the inside of the cowling, because you're always looking at it with the cowl open, trying to figure out why it keeps giving a false signal. And then you close it and there's metal somewhere touching. So you look very carefully along the length of it for chafing or signs where it's touched the metal. And they're bendable. You kind of just bend them out of the way. Most of the time, that's all you got to do. Or replace the little grommet if it went missing. But they're run in parallel because in most cases, you have two loops. Your fire system, before it gives a warning, in order to prevent false alarms, needs to see a fire or an overheat in two loops. Okay, normal operation, they're typically called the A and the B. It has to see a fault on both A and B. If it sees it on just A or just B, it assumes it's, say, a hot spot or chafed or got crimped or crunched. Okay. However, if a loop does get damaged, say your B loop gets a kink in it and that outer shield is able to touch the wire in there and you've got a constant short, the crew has the ability to say, I only want you to look at the A system. And in that case, then a single loop can cause a fire indication, but you have a higher likelihood of a false alarm. And what that's for, it's dispatchability. It allows us to continue to fly the airplane until we can get it somewhere to get that fixed. Okay. Normal operation, two loops, redundant and false alarm prevention, but we can go to a single loop if need be. So I talked about the continuous loop, their damage and break tolerant, all those things. We kind of looked at that. The other type of loop you'll see is a pneumatic loop. And these are basically, think of like a little sealed tube with a pressure sensor on the end. Most of them are filled with helium and then a helium gas, and then they have a hydrogen charged core. And so what happens is when these get warm, that core gives off hydrogen, which increases the amount of gas inside of this tube. As that pressure, as more hydrogen enters the helium tube, the pressure increases to a point where it causes a switch to be activated. Okay. The other thing it does is the switch is actually a two-way switch. If there's too much pressure, it activates the switch. If there's not enough pressure, it activates a switch. If you were to get a hole in one of these, right, you wouldn't want it to be at a point where then it couldn't sense. So it'll sense if the pressure drops to a point where the loop is no longer effective, and it gives you a caution, or it'll fail a self-test kind of situation. Throughout the aircraft, we can have spot detectors. And these come in two basic forms. You can have thermal switches. What's a thermal switch? What have you guys heard of it as? What are they usually made of? Remember what? That's more of a fuse, a thermal fuse, or meltable, because that can't be reset. A switch needs to be able to reset. Bimetallic, I heard the term. You got two pieces of metal that are next to each other. They're going to expand at different rates. When it gets hot enough, it causes that bimetallic strip to bend, and it either opens or closes the switch, depending on the design. Some of them open the switch, some of them close. Okay, kind of. It doesn't latch though. It resets when it's done. A circuit breaker has the bimetallic strip, but then it latches. This doesn't latch. It's going to self-reset when it cools back down. These were, you tried these on the board, the fireboard in there, right? You put the torch against them, the two little things sticking out, it went, but then as soon as you took the fire away, maybe 30 seconds later, it went back to normal. Not even that. I think those were like 5 seconds. Took the loops about a couple minutes. A thermocouple, your other type, is it's still a bimetallic. Don't confuse it. Nothing moves in the thermocouple, remember. The most common are chromel alumel style. And what those do, where you have those two dissimilar metals joined, is they create, as it heats up at that joint, you get a voltage difference between the two different metals. You get a potential. And so you can detect that voltage difference in order to send out a signal. And in both these cases, they're often hooked up in parallel, or the thermal switches are hooked up in parallel like this, where if any one of these switches activates, it's going to send a signal. Thermocouples are in series, and when you have thermocouples in series, they essentially act as one giant thermocouple. But any one of them is going to change the amount of voltage difference from one end to the other for the series. So those are our heat sensing elements. Again, are the continuous loop, the pneumatic loop, and then the two types of spot detectors. Okay, and spot detectors are located often in strategic locations, say at joints between ductwork, or certain areas where fire is more prone inside of an engine compartment near, say, fuel lines and that kind of thing. Or in leading edges, they're along the leading edge of the wing to check for temperature in the wing. Okay. If we want to look for evidence of fire, we can use smoke detectors, and these come in two basic types: light refraction and ionization. Anyone know what kind is shown on here? What's that? Why do you say ionization? No, a little radioactive symbol on it. Okay. So the first type, light refraction, is you have inside, you have a light source and you have a photoelectric cell. So basically a light source is something sensing it. And they can work in roughly two ways. One is where you have the light source and the cell normally pointed at one another. And if you get enough smoke in there, it blocks that light from getting to the sensor. That's the less common form. A more common form is a reflection style. Okay, so that's a smoke disruption style. The other type, light refraction style, is you have a light source and you have a sensor, and it's got like a little labyrinth looking chamber in it, where normally that laser type light source can't bend around the corners to the sensor. But when you get smoke in there, anyone ever see it? You have like a laser shining through smoke, you can see it. So that reflection, it's reflecting off the smoke particles, that gets picked up by the sensor. So that's a refraction style versus a direct disruption style. Ionization is that we have two charged plates. It runs a small current through a couple charged plates. And in the presence of radioactive material, you get a current forming by the electron or the particles coming off the radioactive material are bouncing into those plates, and they cause a current form. But if you get smoke in there, they're releasing these radioactive materials release alpha particles, which are very low energy particles. They can be stopped by a piece of paper. It can be stopped by the outer layer of your skin. But the smoke can also disrupt the alpha particles from getting from that little chunk of radioactive material up to those charged plates. And so there's a certain amount of, when that charge hits the plates, it creates a current flow. There's a certain amount of current it's looking for. And when that smoke gets between the little piece of radioactive material, I think it's usually americium, and the charged plates, then that current drops and it sends a signal that there's smoke present. Okay. Light refraction ones work really well with like thick, dense smoke. Ionization ones work better with like your real wispy, kind of light, thin smoke, almost the kind that makes more of a shimmering effect. So some of your best smoke detectors actually have both in them, where they will pick up two different types of smoke. And that applies to your house too. You can buy both types for a house. And some of the latest recommendations are that you have a dual detector type, because it'll catch this kind catches like smoldering fires really well. That's that thicker smoke. This kind catches the thin smoke you get off. You think of like a raging bonfire where you really can't see the smoke. This is going to catch that faster. So next element, instead of seeing the smoke, is to see the fire itself using an infrared optical sensor. So they see the heat that's coming off. You all got to play with the infrared camera when we did the air cycle machine. These are a very simple form of that. You also tested one of these on the fireboard using the infrared flashlight. And so it basically just sees a heat being energy, the energy being emitted from an object. So if an object's emitting extra energy, more energy than it should, i.e. that object's on fire, this will see that. So it doesn't even have to wait for smoke. However, the limitation is it has to have line of sight. So they don't work real well in a cargo hold where you may not be able to see the smoldering fire or the smoldering heat because it's on the other side of a bag or something. So these are used they can monitor one area, kind of the first year they were used was more of a military and helicopter application, as they would be pointed at the gearbox, the engine gearbox and the propeller or the rotor gearbox. And if the rotor gearbox started to overheat because of something going wrong in it, they would get an advance warning before the rotor gearbox would actually shell out and cause where you'd have to do an auto rotation, hopefully. If it shelled out so bad that it jammed the rotor, you were pretty much out of luck at that point. So hopefully they see that before. And even the factory that I managed maintenance at, we had these to monitor the bearings on our big machinery, where we could see if a bearing was getting hot before the bearing actually went bad. Then you're supposed to take the machine out of service and fix it, but I never got to actually do that. I was just told to run it till it broke and then fix it at 2 a.m. So yeah, other sensing device, combustible mixture detectors. I mentioned these are going to look at concentrations of oxygen and then various fuel sources. And so it doesn't indicate if ignition is present. You can have an explosive or combustible mixture, but as long as you don't have that ignition source, it's not going to burn. But it doesn't take much of an ignition source if you have a truly explosive atmosphere. It can be as much as a little bit of static electricity jumping across one spot to another, or a little tiny fuel level sensor wire that gets chafed in a fuel tank and causes something like TWA Flight 800 that ignited the center tank. So these are being used somewhat there's a little bit of limit to using them in fuel tanks, just because if they get fuel sloshed on them, it can cause them to read wrong. But you can you can have like a suction tube that pulls air off the vent system and runs it by one of these sensors, for instance, to monitor the atmosphere coming out of the tank. It can also be used in a cargo hold, especially if you're carrying hazardous materials or materials that can cause that, to sense for like leaks and that kind of thing. So those are our various sensing devices.